Good day, everyone. Today we will be introducing a new family of Bayesian estimators called linear minimum mean square error estimators. This is a very interesting family because despite the simplicity of its members, these estimators manage to solve the key limitations of the Bayesian estimators that we have discussed so far, and at the same time they allow us to solve complex estimation tasks such as sequential estimation and state estimation in dynamical systems. In particular, remember that LMMSE estimators are given by the conditional mean of the parameters and given the observations, and therefore their computation involves an integral. And of course, that integral can be solved in closed form if the problem is sufficiently simple, but in the general case, we will need to resort to a numerical integration. However, we all know that numerical integration is challenging, especially if the dimension of the variables with respect to which we are integrating is large, right? On the other hand, maximum a posteriori estimators reduce the complexity of MMSE estimators because they don't involve an integral. We just need to maximize the log posterior PDF. However, even that optimization task may be difficult because the log posterior need not be convex. It may have multiple local maxima, right? And in addition, both MMSE and maximum a posteriori estimators require full knowledge of the joint distribution of x and theta, right? Or equivalently to know the prior and the likelihood, right? But this is quite a restrictive assumption because in many practical situations we don't know or we don't have such a detailed knowledge about the joint distribution, so we cannot directly apply these estimators. So to bypass these limitations, today we will be looking at the so-called linear minimum BMSE estimators, or LMMSE for short. An LMMSE estimator is defined as the best affine estimator in the BMSE sense. Okay, so the name says linear, but they are not necessarily linear. They are affine. Okay, this can be illustrated in this Venn diagram. If this is the family of all estimators of all functions of the data, essentially, we restrict our attention to those estimators that are affine functions of the data. Okay, and within that family, we seek the estimator that minimizes the BMSE. So this criterion reminds us of the one that we used or the one that defines the best linear unbiased estimator, right? This one was the estimator that minimizes the non-Bayesian MSE among the class of all linear unbiased estimators. The price to be paid by confining ourselves to a strict subset of the class of all estimators is that the resulting VMSE will not be necessarily as low as the VMSE of the LMMSE estimator. However, we gain along multiple fronts. So, for example, the LMMSE estimator is much easier to compute because it is just an affine function of the data. And in addition, we don't require full knowledge of the joint distribution of the data and the parameters. We will just need to know the first and second order statistics, specifically means and covariances. And in addition, the LMMSE estimator coincides with the MMSE estimator when the MMSE estimator is affine, right? So this can be seen here. The MMSE estimator is the best among all possible estimators in the BMSE sense, right? So when this MMSE estimator is inside this yellow set, it is obviously also the best among all possible affine estimators, right? And this is not a rare case. As we saw when we studied MMSE estimators, these estimators are affine for the Bayesian-Gaussian linear model, right? And therefore, in this situation, we do not lose anything by doing LMMSE estimation. This lecture will make extensive use of the calculus of covariance matrices. That's why I list here a number of properties that we will be using in this and upcoming lectures. These are typically studied in probability theory courses. I recommend at this point that you stop the video and try to prove these identities, because I warranty that following this lecture will be difficult for those that have forgotten them. And most of these proofs can be done in just one line. They just involve applying the definition of a covariance matrix. Okay, so as an illustration of the procedure, these are the solutions to two of the required identities. In this first one, we have the covariance of x and a linear function of y. So as we said, we just need to apply the definition of a covariance matrix, right, which is the expectation of the first random vector minus its mean times the second random vector minus its mean transpose. Okay, and here we just use the fact that the expectation operator commutes with linear functions of the random vectors, and to write it in this way, now we can just take b, a common factor here, and apply the properties of the transpose, right? So the transpose of a times b equals the transpose of b times the transpose of a, right? So just by that property, we can express this expectation in this way, right? And now this is just again linear function, expectation of a linear function, which is just the linear function of the expectation, right? So this is just the covariance of x, y times b transpose, okay? And here we just have the covariance of x and a vector that is divided in two blocks, right? This is typical notation. This vector contains the upper entries of this entire vector here, and y in this case contains the lower the entries at the bottom. Okay, so again we just apply the definition. So we have the expectation of x minus its mean times this vector minus its mean, which here we denote the mean of z as mu z and the mean of y as mu y. Okay, so now if we transpose this vector, we obtain this row vector. Okay, and now just by applying by multiplying this column vector and this row vector, we obtain this matrix here. Okay, and which is divided in blocks, right? So this is the left block of the matrix and this is the right block of the matrix. Therefore, what we have obtained here is the covariance of x and z, and here we have obtained the covariance of x and y. Okay, so it's very easy, but we just need to be comfortable with the definition of the covariance, and be careful when decompose matrices and vectors in blocks. Remember that operating with blocks, right, is like operating with scalar entries, but we just need to be aware that the product of matrices is not commutative, right? So now that we are comfortable with the calculus of covariance matrices, we can delve into LMMSE estimation. So suppose that we are given one of these pieces of information. We can be given either the joint distribution or the prior and the likelihood, or simply the moments, the mean of the data and parameters, as well as their covariance. Okay, and so given this information, our goal will be to find the best affine estimator in the BMSE sense. Okay, the one that minimizes the BMSE. And this will be represented in this way: LMMSE estimator of theta and given x. Just a bit of notation to simplify our expressions. We will denote the mean of x by mu sub x and the mean of theta by mu sub theta. Regarding the second order moments, this is the covariance of a vector that results from stacking vertically the data vector and the vector of parameters. And just by the definition of covariance, this is the expectation of this vector minus its mean times its transpose, right? So this is we can just combine add these vectors to obtain this product of a column vector and a row vector here, both of them again defined in terms of their blocks. And one can just multiply these two vectors to arrive at this matrix. Okay, this is a matrix with 4 blocks. The expectation can go inside each block, and therefore what we obtain is that this is the covariance of x. Okay, this is the covariance of x and theta. Okay, denoted in this way, and so on. Okay, so just again to simplify our expressions, this will be denoted as cxx, this as cx theta, and so on. As per the problem formulation in the previous slide, we need to find the affine estimator that minimizes the BMSE. So to that end, remember that any linear function can be written as a matrix times its input. And we say that a function is affine if it can be written as a linear function plus a constant, okay? So affine functions constitute a more general or a larger family than the family of linear functions, right? Actually, all linear functions are affine, right? But obviously the opposite is not true. So let's start by using the fact that the LMMSE estimator is affine, right? And it is an affine function of the data, right? And therefore, the LMMSE estimator of theta given x can be written in this way for some matrix A and some vector B. Here we need to be careful with the dimensions. Remember that we had n parameters, okay, and n samples. Therefore, this matrix needs to be m by n, okay, and this vector needs to be of length m. Remember that all vectors are column vectors according to our notation. The goal is, therefore, to find A and B such that the BMSE of this estimator is minimized, okay? And so this means that A star, the A and B, the optimal A and B are the minimizers of the BMSE, right? And therefore, just by using the definition of the BMSE, they are the minimizers of this expectation here. We can just substitute this here, and therefore we have to minimize this expression. Let's start by minimizing it with respect to B. So we take the gradient with respect to B. So the first step is to exchange the order of the expectation and the gradient. Then we can apply the chain rule and to obtain this expectation here. So remember that there are some review notes in the same folder as the slides that you can use to refresh your knowledge of gradients, Jacobians, Hessians, the chain rule, and so on. That's very important. And finally, just by taking the expectation of these random vectors here, we obtain that this is the gradient with respect to B. If we set this gradient equal to 0, we can solve for B, and we obtain this optimal B, right? So the B that minimizes the BMSE. One can now just substitute this expression here, and that means that our LMMSE estimator is can be expressed in this way, okay? So we see that this is the prior mean, okay, plus a linear function of this normalized version of the data, right? So it is normalized so that it has 0 mean. So it's essentially correcting for the mean of x. And one can also substitute this expression here, right? And this means that the resulting BMSE is given this expectation here. Okay, so two remarks are in order at this point. First of all, we see that if the mean of the parameters and the mean of the data are 0, then this vector is 0 and this vector is 0. This means that the LMMSE estimator is just a times x, so it is a linear function of x. Okay, so then in that case we don't need to make the distinction between affine and linear. However, if the means are not 0, right, what the LMMSE estimator does is to simply correct for the means, right? So you can see that here we have the parameters minus their mean, and here the data minus its mean, right? So this means that applying the LMMSE estimator on data and parameters with non-zero mean, it is exactly the same as first subtracting their means, right? Then applying the LMMSE estimator, and after that we just add the means back when necessary. So this means that we often assume, that we can assume that the means are 0 without any loss of generality, and this is what we will do sometimes. Okay, so this is the BMSE after minimizing with respect to B. Now the next step is to minimize with respect to A. Since A is a matrix, one cannot directly take gradients here. So what we will do is to decompose A into its rows. So we denote the rows in this way. We write a transpose here because remember, for us, little lowercase letter with an underscore denotes a column vector. Okay. So the optimal A is the one that minimizes this expectation, which just by the definition of the Euclidean norm can be written as this sum of squares. Okay. What we observe now is that this objective function here is the sum of capital M terms, right? And each term depends on one of the rows, but each row shows up only in one of these terms. Therefore, minimizing this objective is the same as minimizing separately each of the summands in this expression, right? And therefore we can decompose this optimization problem into capital M optimization problems of this form. Okay, so we optimize for each row separately. Since now the optimization variable is a vector, we can take the gradients. Okay, we can take the gradient. So in this case, applying the chain rule here yields this gradient, this expectation here. Just rearranging terms, we arrive at this expression over here. Okay. Now one can just recognize that this is the covariance of x and the mth parameter, okay, which as per our notation can be written in this way. Okay, note that this will be a column vector, okay, and this is nothing but the covariance of x. Okay, so matrix times a column vector here. If we set this gradient equal to 0, we obtain this equation here. which in principle we can solve for each row. But let us solve it for all the rows at the same time. So to that end, one can transpose both sides of this equation here to obtain this equation, okay? And this, if we just stack vertically these terms for all values of m, so for all rows, right, we obtain precisely this matrix here. And if we do the same with the right hand side, we obtain this matrix, okay? And therefore one can just recognize that this is A, okay, and this is the covariance of theta and x, so it can be written in this way. And now from this equation we can just multiply both sides by the inverse of cxx, and we just obtain this, the optimum A. Therefore, just by using our optimal A and the optimal B that we found in the previous slide, the LMMSE estimator can be written in this way, right? So the prior mean plus this linear function of the result of normalizing the data to have a zero mean, right? And this will be the matrix that multiplies that normalized data. As promised, note that this only requires first and second order moments, right? Means and covariances. No other information about the joint distribution is required. And this constitutes a big advantage of LMMSE estimators, right? Because it is often the case that we don't have access to the full, to complete information about the joint PDF of x and theta. And note that this expression is exactly the same as we obtained when we were deriving the MMSE estimator of a parameter vector given a data vector when both of them are jointly Gaussian, right? So this and in fact this expression is very important. I think I suggested at that point that to try to memorize it. It's not that difficult. Here we have it's natural to have here the prior mean, okay? And this term here can be, one can remember it perhaps just visually by seeing that here we have x, 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 and x, right? But also by it is a very good trick to look at the units, right? Because that help us detect if we have missed any ingredient, right? So think, for instance, that theta is in meters and x is in seconds, right? Therefore, the units of this covariance are meters times seconds, right? The units of cxx are seconds square, but we invert it, we get seconds to the -2, okay? And the units of these are seconds. Therefore, we would have meters times seconds divided by seconds squared, which means meters, right? So this check will help you, for instance, detect that you have forgotten to write this inverse here or something like that. Note that this one cannot be inverted, right? Because this matrix need not even be square. Okay, so the inverse obviously goes here. So with this, perhaps with these observations, now you can remember this expression. And it is a very important observation, and that this also shows that LMMSE estimators exploit the information in the correlation, and they don't exploit other information that is not in the correlation, right? So if, for example, this C theta x, this correlation is, or covariance is 0, right, then the LMMSE estimator of theta is exactly the prior mean, right? Therefore, this means that the data is not used at all, even if x and theta are dependent. If they are uncorrelated, then the LMMSE estimator cannot do anything to help us. So this is the caveat of LMMSE estimators. So let's put this into practice. Suppose that our data is given by a DC component plus a noise, and we have a prior on a uniform prior on the DC level, okay, and the noise is white, okay, with variance sigma squared, and independent of the parameter. So given x and this a0 here, and also sigma square, we would like to estimate a. The LMMSE estimator of a given x is as per the expression that we now remember by heart, given by the prior mean of a plus this expression here. So we just need to obtain each of these quantities, okay, and substitute them here. Let's start by mu a, okay, and a is a uniform random variable in this interval. The mean of a uniform random variable equals the arithmetic mean of the endpoints of the interval where it is defined, and therefore this is just 0. Regarding x, okay, we can just use this expression here and just take expectations, and so this we arrive at this where the expectation of a is 0, as we saw here, and the expectation of w is also 0 by hypothesis. Therefore, the mean of x is also 0. Okay, so at this point we already know that our LMMSE estimator will be a linear function of the data. Regarding this covariance, we apply just the definition of a covariance matrix, okay, and now we can use the fact that mu a and mu x are 0 to write it as the expectation of this product, and then one can just substitute this expression here, okay, and this just yields this. But now here we can see that we have the expectation of A and W transpose, but A and W are independent, which means that they are uncorrelated, and therefore the expectation of their product equals the product of their expectations, which are 0, okay, and therefore this term just disappears, and we are left with the expectation of a squared times this row vector of all ones. So now we need to obtain this expectation of a square, okay, and since the mean of a is 0, we can subtract it from a without changing anything, right? And this is nothing but the variance of a, right? And just as we know from probability theory, the variance of a uniform random variable is just the difference between the endpoints squared divided by 12, and this yields a0 squared divided by 3. The covariance of x can be found in a similar way. We just use this expression here and use now the fact that this vector 1 times a and this vector are independent, therefore uncorrelated, which means that the covariance of their sum equals the sum of their covariances, right? And now, just by using one of the properties that we reviewed earlier today, this covariance is given by this matrix here, and this covariance is sigma square I. Just by substituting these quantities here, we arrive at the expression for the LMMSE estimator, which, as we anticipated, it is a linear function of the data. But whenever we see something like this, namely an inverse of some identity matrix plus a column vector times a row vector, we can apply the so-called matrix inversion lemma, okay, which provides this identity here. So this is a well-known fact in linear algebra. There will be a homework where you will have to derive this expression, but in general, whenever you need it, you can just go to Wikipedia and find it. So if we just apply it here, so this would be our A, this will be U, this will be V, and this will be V, right? We do this, we obtain this much simpler expression, okay? Where now we have here the sample mean of the data. So remember that the sample mean of the data is a sort of very reasonable estimate for the DC level. In fact, this is the blue estimator of A. So this is x bar. It would be our estimate or natural estimate of the DC level if we didn't have any prior information. But the LMMSE estimator, what is doing is to multiply that estimate that is oblivious of any prior information with this coefficient, which is less than 1, right? And therefore, what is doing is shrinking the sample mean. And why does it make sense? The reason is that we have indicated here that the mean of the prior mean of A is 0, right? So what this expression is effectively doing is to bring what our data says closer to what our prior information is saying. So again, we see this interplay between prior information and data that Bayesian estimators leverage. And in particular, see that if our data has very little noise, right, this coefficient will be close to 1, and therefore we will be relying to a great extent on what our data says. And in contrast, if the data is very noisy, then this will be close to 0, and the estimate will be close to 0 as well. So, everything is makes sense. And note an important property here. This number here can be outside the interval where we know that A is contained, right? And this is a consequence of the fact that this is a linear function of the data. And any linear function that is not zero will somewhere get out of this interval for I mean, some depending on the data, right? You see that the data is not bounded, not necessarily bounded at least, right? And therefore, just this number can be anywhere. So, I mean, of course, if we were in a practical application, we could take this estimate and after we compute it, if it is out of this interval, we just bring it inside the interval by setting it to A0 if it is greater than A0 and setting it to minus A0 if it is less than minus A0. But I mean, that's of course like what a practitioner would do. Let us analyze the performance of LMMSE estimators. And to that end, we define the error as always in this way. The expectation of the error can be found by substituting here the expression that we know for the LMMSE estimator, okay? And just by applying the expectation operator to each term, we can write it in this way. And now one can just observe that this is just mu theta, so these two terms cancel, and this is mu x, so these two terms cancel, and therefore this is 0, which implies that the LMMSE estimator is unbiased. Okay, so just it's a desirable property as we know. To obtain the covariance, we apply the definition of covariance matrix here, and note that this expectation is 0, as we just proved. Okay, and now one can apply the same procedure as here to write this expectation in as the product of these or the expectation of the product of this column vector and this row vector, okay? And one can now just expand this product, okay, to obtain this long expression here. But one can recognize that this is nothing but c theta theta, this is c theta x, and so on, okay? And this can be now simplified with these two matrices cancel, and we can just write this final expression for the covariance of the error. So again, this expression showed up when we looked at MMSE estimators for Gaussian or jointly Gaussian parameters and data, okay? And I said at this point that it was good to remember this expression. So it's not that difficult. Here it's important to see that there's a minus sign, right? This is very intuitive because this matrix captures the uncertainty after we see the data, whereas this first matrix captures the uncertainty before seeing the data, right? The prior uncertainty, and therefore the posterior uncertainty should be less than the prior uncertainty, right? Observing data should never increase our uncertainty, okay? And this term can also be remembered by using again, I mean, like visually, but also by checking the units, okay? In particular, this product of these two matrices is the same as shows up in the expression for the LMMSE estimator. And now it is very interesting to look at the covariance of the error and the data, okay? This, just by the definition of covariance, is given by this, and again by substituting epsilon with this expression here, okay, and noting that the mean is of the error is 0, we can write it in this way. And just now expanding this product, we find that this is c, this term times this term is c theta x, and here we will have this c theta x times cxx inverse times the expectation of this product, with which is nothing but cxx, right? And this cxx and cxx inverse and cxx cancel, okay, and we have this matrix minus itself, which is 0. So what this is saying is that the error is uncorrelated with the data, and this will be a mantra that we will be repeating over and over. It will be a very useful property in the future when we talk about sequential estimation or the Kalman filter. But instead of using the word uncorrelated, you will often hear people saying that the error is orthogonal to the data. And this stems from an interpretation in terms of a vector space of random variables. And it is not necessary to understand the rest of the course. I'm just going to briefly describe this interpretation now, just for completeness and for those of you that like to think mathematically. So the idea is that one can think of a vector space where its elements are random variables, right? We can add random variables and we can multiply them by scalars, and therefore they just form a vector space. They satisfy the properties of a vector space, right? So this means that we can think of our parameter. In this case, let's, for simplicity, assume that we have a single parameter. Okay, so we identify it with a vector in that space. Okay. And the LMMSE estimator is a linear combination of the samples, right? And the samples are random variables as well. Therefore, the LMMSE estimator is another random variable, and it can be represented or thought of as another vector in that space. And since each of these random variables of the samples lie in this space as well, we can think of the span of these vectors here, okay, and that will form sort of a hyperplane in this space, okay, and the LMMSE estimator will be one of the vectors in that hyperplane. So what the LMMSE estimator does is to find the linear combination of the samples that minimizes the BMSE, right? This is because here, for simplicity, we are assuming that the means are 0, right? And therefore the LMMSE estimator is linear, right? So this can be equivalently written as the minimization of the expectation of this square difference here. And this can be thought of as a distance, right? If or a square distance, if we define and we choose as our inner product the expectation of the product of random variables, right? So this is essentially a projection of this random variable here onto this hyperplane, okay? And as we know, projections will yield a vector that is orthogonal to the hyperplane, okay? And therefore here we see that epsilon is orthogonal to all to this hyperplane, and therefore it is orthogonal to all vectors in their hyperplane. Specifically, is orthogonal to all the samples. Okay, so it's a neat interpretation, but as I said, it's not necessary to follow the rest of the course.